Which numbers are hypotenuses of right-angled triangles? Which z arise as r squared plus s squared, right? And we made these tables and we made some observations. So did you guys do it? Did anyone play with it and make any observations? You made some? You made a table? So which z's did you find?
So what I do is I try for the diagonal, the entire diagonal, find the what the conversion to that, and then I look at the off diagonal and just kind of make what you said.
Okay. Did anyone notice any patterns in what numbers seem to appear, or maybe I'm foreshadowing a little bit what numbers didn't appear? So 0 is the sum of two squares because it's 0 plus 0 squared plus 0 squared. 0 squared plus 1 squared is 1. 1 squared plus 1 squared is 2. Doesn't seem to be a way to get 3. Devendra, do you want to say something? Some multiples of 3 didn't seem to arise, although 9 is 3 squared plus 0 squared. 4, of course, is 2 squared plus 0 squared. 5 is 4 squared plus 1 squared. 6 is missing. 7 is missing. How about 8? 4 plus 4. 9 is 9 plus 0. 10 is 10 is sum of two squares. 9 plus 1. 11 missing. So missing numbers, missing z's. We're missing 3. We're missing 6 and 7. We're missing 11. And this is where you put your pattern searching hat on. That's what human beings are very good at sometimes, is searching for patterns. Now this problem, this is why people think number theory is a study of prime numbers. It's not the study of prime numbers, it's the study of numbers. But so often, questions about whole numbers end up being reduced to questions about prime numbers. So let's look at some of these primes. So this is a prime, this is 2 times 3. Is 12 going to be there? Is 12 a sum of two squares?
Oh, yes. No.
12 isn't there. So 12 is 4 times 3. So as Devendra said, some multiples of 3 are missing. Is 13 there?
13, 16.
Say it again.
13 through 16.
13 is there or isn't there? 13 through 16 aren't there? How about 9 plus 4?
Okay,
9 plus 4 is 13. So 13 is there. Let's go a little farther in the data. How about 14? What's that? Not there. 14 is missing. 14 is 2 times 7. 15? 15 is missing. So Karen, you did this? A little bit.
How far I can go.
Okay, let's just keep going a little farther. So as Devendra noticed, there's a bunch of multiples of 3 that are missing, but there are also some multiples of 3 that are not missing. Right? Let's just go a little farther. 16, well, it's already itself a square, so any square is itself plus 0. So that's kind of easy. How about 17? 4 squared plus 1. 16 plus 1 is 17, so that's there. 18? Why? 9 plus 9. 9 plus 9 is 18. So that's another multiple of 3 that makes it in. How about 19? No. So, okay, so I have to, when I assign something as homework just for fun, I actually have to assign it as homework, right? Because it's not going to get done otherwise. Is that, no, just, reality, right? You guys have lives, you have things you want to do over the weekend. Taking a table of squares and adding them is not one of them, unless I force you to. So, mental note. 19 is not on the list. 19 is not a sum of two squares. How about 20? 16 plus 4, 20 is on the list. 21? Not on the list. 21 is 7 times 3. Okay. There's a very easy thing that we can observe. Although it takes a little bit of, I'm trying to get someone to notice something. Karen?
The only multiples of 3 that are in Z have squares of 3 in them?
Yes. Yes, excellent point. The only multiples of 3 that do appear in the Z's, in the list of Z's that we see, have multiples of 3 squared, not just 3. 3 squared is there, but anything with just a single 3 is in the missing list. That's a good observation. There's something special about 3. In fact, there's something special. Here's an easy lemma. Notice these numbers: 3, 7, 11. What is that? 12, 14, 15, 19. Some of these are in a progression. 3 to 7 is a skip by 4. 7 to 11 is a skip by 4. 11 to 15 is a skip by 4. 15 to 19 is a skip by 4. 19 to 23 is a skip by 4. Say it again.
Is 27 also missing?
27 will also be missing. And 27 is a number that's 3 cubed. So it has a 3 square in it, but has a 3 to an odd power in it. So there's something very fundamentally bad about the numbers that are 3 mod 4. So we haven't talked about modular arithmetic yet. So let's spend some time in modular arithmetic, but first let's prove this lemma, which is that if Z is congruent to 3 mod 4, now, and what this means is when you divide Z by 4, the remainder is 3. In other words, when you take 23 and you divide it by 4, well, 20 is a multiple of 4, so your remainder is 3. So 23 leaves a remainder of 3 when divided by 4. That's what this notation means. We're going to talk about that in a minute in more detail. So if Z is 3 mod 4, then Z is not a sum of 2 squares. That's the first kind of basic lemma that I want us to understand. Okay? Want to think about how you would prove it? So first let's talk about modular arithmetic. So we say, so I have to explain what this is. The definition. It turned out that a very useful thing to be able to say, so A is congruent to B mod C. A, B, and C are integers. If and only if, this is the definition, A is congruent to B mod C, and you write this triple equal sign. This is a triple equal. This is meant to be a 1, 2, 3. 1, 2, 3. Triple equal sign. Congruent. A is congruent to B mod C. Does anybody know what that means? Debendra?
C divides the difference A.
Exactly. If C divides, the difference B minus A. Okay? So here are some exercises for you to do right now. What is 34 mod 5? What is 27 mod 3? What is 42 mod 11? So what I mean by this is any number has a, so this should be a number, 34 mod 5 is just 34. 34 is congruent to 34 mod 5. What I mean is, what's the simplest? So this should be a number in the range 0 to 4. And this should be a number in the range 0 to 3, and this should be a number in the range 0 to 11. 0 to 10, because 11 is equivalent to 0, is congruent to 0, mod 11. Okay? Take 10 seconds and see if you can work out all of these and give me a hand when you're done. Do we understand modular? What the definition of modular means? Give me a thumbs up when you're done. Okay. A couple people are still working. Okay, can I pick on Drew?
Yeah.
What did you get?
34 mod 5 is 4.
This you got 4 because 30 is a multiple of 5, so 34. 27,
0.
0 mod 3 because it's a multiple of 3. And 42, this is the tricky one. Right, I would say 44 is a multiple of 11. And this is negative 2, and negative 2 is 9. So this is congruent to 9 modular. Okay? Does everybody see what modular arithmetic is? Or what the definition of modular is? Now I keep saying modular arithmetic. The amazing thing about this, completely non-obvious, so this is the amazing thing. Let's call this a lemma. You can do arithmetic before or after taking mods, and you'll get the same thing. So, how do I want to put this? Well, there's a fancy way of saying this, which is that mod is a ring homomorphism. We don't know what that means, and never mind. So, how do I want to say this? A plus B mod C is congruent to A mod C plus B mod C. And A times B mod C is congruent to A mod C times B mod C. So let's just see a few examples of this lemma before we prove it. So examples, I don't know, 5 times 7 mod 4. Work out 6 times 8 mod 3, and work out 9 times 10 mod 7. Okay, so what I mean by this is first multiply 5 by 7, then reduce mod 4. Oh, some of these should be pluses. I want to illustrate both of these things. So let's make that a 5 plus 7. So first work out 5 plus 7, then reduce mod 4, or reduce mod 4, and then add. First multiply, then reduce mod 3, or first reduce mod 3, then reduce mod 3, then multiply. Karen?
Is it convention not to put parentheses around the A plus B, or?
Yes, so the mod C, the convention is that mod C kind of pulls all the way out of the equation. So it's kind of floating around somewhere to tell you that you're doing arithmetic mod 7, but it doesn't really matter where it goes. In fact, some people would really disagree with what I've written here, because it looks like I want to multiply mod C by B, but that's not what it's not. This is kind of bad notation for some much simpler concept, which hopefully will be illustrated when you do this exercise. So take 3 minutes, and give me a hand up when you have all 3 answers in. I mean, there's 3 questions, but really each question is 2 parts. First, do the arithmetic, then reduce, or reduce, and then do the arithmetic. Do you get the same thing? Got it? Give me a hand when it's done. Alex got it. Yeah. And talk to your neighbor if you want to. Cheat, look on their page.
Okay. Let's see.
see, Kevin. Almost ready to do it all together? Some people are still working. Okay, let's do it. 5 plus 7. 5 plus 7, what is 5 plus 7? 12? 12. So this is 12, and 12 is a multiple of 4. On the other hand, 5 is 1 mod 4, and 7 is 3. So 1 plus 3 is 4, and 4 is 0 mod 4. So you see, it's not that this number is going to come out to the same number when you do the reduction once. You have to keep reducing. Okay? You wind up, they're in the same residue class. These are called residue classes. Where should I put these words? So what we say is that A and B are in the same residue class. Okay, that's what, or A is congruent to B mod C. Okay. So is that clear? We got 0 when we first added and got 12, and we also got 0 when we first did the modular, reduced mod 4, and then added. How about 6? 6 times 8 is 48. 48 mod 3 is 0. 6 is mod 3, 0. 8 mod 3 is 2. 0 times 2 is 0. 0 and 0. 9 times 10 is 90. 90 mod 7. 91 is 70 plus 21. So 91 is a multiple of 7. So this is -1. And -1 is the same as 6. On the other hand, 9 is 2 mod 7. And 10 is 3 mod 7. 6. Okay? You want to take a minute and see if you can prove this lemma? So proof of, let's see, we have 2 lemmas that are hanging around. Let's call this lemma 2. Lemma 2, here's lemma 1. We have to come back and prove lemma 1. Lemma 2, so proof of lemma 2. So if I take the residue class A plus B mod C, and I take the residue class A mod C, and I take the residue class B mod C, I add these 2 together, I get the same residue class. So you can think about this in a variety of ways. Oh, let me just leave you alone for 5 minutes to think about how you would prove this. Now you've seen it in action, you know what it means. How do you prove something like this? There's kind of a very down-to-earth way of thinking about these using representatives. That's what we did here. We chose a nice representative. And there's a more fancy way, which is to think about the entire class of all the numbers that are congruent to 4 mod 5, for example. And that's an infinite set of integers. It's an entire arithmetic progression of integers. Either way, so there's 2 ways of proving this lemma. I leave it to you to see which one you, maybe we'll do it both ways, just to practice both modes of thinking. Take 5 minutes. When you've written what you think is a proof, give me a thumbs up. And also talk to your neighbors and argue and see if you can make sense of it. other classrooms you have to get people to stop talking. Argue with each other. Give me a thumbs up if you have a proof. Is that a maybe? That's a wrist up.
Oh,
No, that's not a thumb up.
no, it's not.
Daniel, is that a maybe or no? Well, let me just write down what I said before. The residue class, so a representative for A mod C is, so what's a number that's A mod C? Well, first of all, A is A mod C. But any representative, any number of the form A mod C is A shifted by a multiple of C. If you change A by a multiple of C, if I take C times some integer and I add A to it, I get the same residue class, mod C, because when I divide by C, I still get the same remainder. Right? So that's what I mean by a representative for A mod C is this, and similarly, representative for B mod C is B plus C times some other number. That's supposed to be an M. So what? Karen, you see something?
I did a proof, but not with representative class. So I didn't
Okay.
go down to earth one.
Okay. Oh, this was supposed to be the down to earth one. Okay, tell me what you said.
Okay, so you have A and B and C.
Yes?
Great. So A is equal to Cm plus K for Mk natural numbers, and B is equal to Cm plus L for NL natural numbers.
Great, let's do Karen's proof. Karen is saying A is equal to Cn plus K. So K would be this representative, another representative for the same class. But K, now you're thinking of K as between 0 and C, 0 and C minus 1. And B is
Cm plus L.
Cm plus L. Great, love it.
So A mod C is equal to K.
Uh-huh.
And B mod C is equal to L. So A mod C plus B mod C
Mm-hmm.
is equal to L plus K mod C.
Okay. How did you get that?
Oh. With the, so the statement that I was going to prove is that A plus B mod C is equal to A mod C plus B mod C, right? So I'm doing the right side of the equation, and making it equal to something, and then I'm gonna do the same thing for the left side of the equation and see if I can get them to be equal to each other.
Okay. I'm almost with you. So say it again. A plus B mod C is.
No, A mod C plus B mod C.
I see. I started on the wrong side. A mod C plus B mod C
Is equal to L plus K mod C.
is equal to L plus K mod C. Okay.
Am I allowed to make that leap?
Well, it is a little bit of a leap.
Adding the mod C at the end?
It's a little bit of a leap because remember, we might have to do one more mod. And so how do we know that we're getting the same thing? Tell me again. Andrew?
If you do like K plus L plus C times N plus N, then wouldn't you see it as representative?
I think you're saying let's just do A plus B. What is A plus B as integers? Right? What is A plus B as integers? it's c times n plus k plus c times m plus l. And the thing to notice is that this is k plus l plus c times n plus m. Devendra, is that what you were going to say?
Time. So what I do is I just like sort of represent this for each term on both sides. I'm going to show that the difference is divisible.
Okay, great. Great. So you can choose. So Devendra is saying something. Let's see. This was Andrew. This was Andrew. Which is just look at the integers themselves. A plus b as an integer is c times n plus k, because that's what a is. This is a. C times n plus l, that's what b is. But then if you switch them around, you get k plus l plus some multiple of c. So this is why the residue class, when you reduce a mod c, you get k. When you reduce b mod c, you get l. If you reduce a plus b mod c, well, this is a multiple of c. So whatever the remainder is here, that's the residue class. And Devendra is doing something else. He's saying, well, if a, so again, keeping this kind of notation, so c divides a minus k, and c divides b minus l. Therefore, c divides a minus k plus b minus l. Does that make sense? If this is a multiple of c, and this is a multiple of c, then their sum is a multiple of c. And this we can write as a plus b, a plus b minus k plus l. In other words, a plus b is congruent to k plus l mod c. So 3 different ways, all totally valid. This is the one that you might have to think about a little bit more, because you might have an extra thing to do. So 1 plus 3 is 0, whereas these two we're back in the realm of integers. Okay? And there's one more point of view, which is, so this again is always using representatives, but actually maybe a higher point of view, or a more abstract point of view. Maybe you don't like abstraction right now, but it might eventually make your life easier if you start getting used to using it. A lot of things get simplified. So more abstractly, a mod c really means a plus c times all of the integers at once. So it's this entire arithmetic progression of a plus c, a plus 2c, a plus 3c, a plus negative 1c, a plus negative 2c, all at once, this entire arithmetic progression. That's the whole class a mod c. Does that make sense? So when you're adding, so this might seem really weird because now that you have infinitely many numbers, and you're going to add a mod c plus b mod c. Now you're adding infinitely many numbers. So this is a plus cz. So that's all the numbers in that arithmetic progression, plus b plus cz. And this is a plus b plus, now this is c times any integer, and this is plus c times any integer. Well, c times all integers plus c times all integers is just c times all integers. And that's what this a plus b mod c as the entire class represents. Does that make sense? So it's a slightly, it's a weird thing to do, to take an entire arithmetic progression and add to it another entire arithmetic progression. But hopefully you see that it just, if you prefer, you can think about representatives, one representative at a time, or you can think about the entire class. So this is why addition works, modular addition. Why does modular multiplication work? So the lemma, where is this lemma? It's all the way back here. The lemma is that both addition and multiplication you can do before or after taking residues. So we worked out addition in a variety of ways. We have the Karen way, the Andrew way, and the Devendra way, and the abstract way. How about multiplication? You want to take 5 minutes now that we've seen that? Take 5, see if you can prove it all 4 ways. And again, talk to your neighbor, argue. Have you guys been getting together in groups to do your homework? A little bit? Not really? No? You just do it, it's too easy? I should make it a little harder?
No. It's like, sometimes.
It's good to get into study groups.
Speaking of homework, are we
Yes.
allowed to assume that Pythagorean triples are pairwise coprime?
We did prove that. So anything we proved in lecture.
We're allowed to use it. It's fair game for anything.
Yes.
Okay.
So,
Anything we proved in lecture, you can just quote. As we proved in lecture.
so we can say actually flip this line because these guys.
We have proved that, so yeah. I don't remember what the exercises were anymore, but I think. Did I ask you to prove that?
No. But there was a problem where it would have helped, so I wasn't sure if we could use it.
Uh-huh.
Yes. Exactly.
I have a question.
Yeah. You come.
Whether A is equal to A mod C is associated
You can think of it that way. Yes, that's one way of thinking about it. If A mod C is just the remainder.
So why can we write A equals to C, A plus C times Z?
So this is another way of thinking about this. This symbol can mean a variety of things, and they're all equivalent. So any number here will have the same remainder when divided by A. So you can think about this is something more abstract happening here, which is you can think about the map of taking A and reducing it mod C, which means find the remainder. This is the pre-image of all the numbers that have the same remainder mod C. The pre-image under that map. In other words, let's make this a little less abstract. What is 1 mod 4? 1 mod 4 is 1, right? I mean, let's do this example. The residue class 1 mod 4. Well, 1 mod 4, what's the remainder when you divide 1 by 4? 1. Right? This is 1. 1 is a representative for the class. But you can also think about all the numbers that leave a remainder of 1 when divided by 4. So then this can also be represented by 1, 5, 9, 13, 17, -3, -7, -11. Okay? These are all the numbers simultaneously that leave a remainder of 1 when divided by 4. So you can think about both. You can think about A mod C as being both. It's what the remainder is, which is just one number, between 0 and C minus 1. Or you can think about what are all the numbers that will give you that same remainder. You can think about them at once. So slightly takes some getting used to. Think about that, right? Okay, we got the times? So if we have a representative, if A is K plus N times C, and B is L plus M times C, then A times B is k plus n times c times L plus m times c. Is this how you did it? How many did it this way? 1 or 2, 3, 4. Okay, the hands are coming up. Okay, and then you just multiply it out. So this is k times L plus, well, a bunch of things that are multiples of c. So k times L is the first thing. Then I have k times m. And then I have L times n. And then I have n times m. And the point is, these are all multiples of c. And so it's just k times L. K times L might not be reduced itself. You might have to reduce it again, but any representative will do, right? So that's one way of thinking about this. Another way of thinking about this is C divides A minus K, and C divides B minus L. Therefore, well, C divides the product. But that doesn't really work, because actually C squared divides the product. So there you have to do, did you try it this way, Devendra? This was your method. The point is, if C divides A minus K and C divides B minus L, then then C divides A times B minus K times L. Why is that true? Because if C divides A minus K, then A minus K is some multiple of C. And if C divides B minus L, then B minus L is some multiple of C. And then this argument tells you that K times L, that A minus B, A times B minus K times L is also some multiple of C. Okay? So that method worked in addition. It doesn't work as well unless it's coupled with this calculation in multiplication. So you learn something every time you prove the same theorem 3 different ways, you actually learn something about the proof. Okay? Does that make sense? And finally, how about this way? This way of thinking about it, the more abstract way. You take the entire arithmetic regression. I mean, it's the same proof, right? You take the entire arithmetic regression, which means any integer multiple here, any integer multiple there, and you get some integer multiple, and other integer multiples. One of the multiples is 1, so you get 1 times any number here. And then you get to shift things around. Okay, are we clear on that? Yes? So, we understand that modular arithmetic, so here's again this lemma that we're trying to prove. Modular arithmetic is arithmetic. You can do arithmetic. You can add and you can subtract and you can multiply. We haven't talked about dividing. Dividing is a funny thing in the integers, right? You can't divide 2 by 3 and get an integer. Modular arithmetic sometimes lets you do it anyway. We'll come back to that. But let's go back to this. Let's go back to the original question about what numbers are sums of 2 squares. So I claim that if z is congruent to 3 mod 4, then z cannot be r squared plus s squared. So let's look at this equation, mod 4. So proof of lemma 1. Look at z is equal to r squared plus s squared, mod 4. Remember, we can multiply and we can add in modular arithmetic. So what are the possible residue classes, mod 4? So r and s. Here's a little table. Let's do, how do I want to do this? Well, we'll do a table of r squared and s squared. So if r is 0, 1, 2, or 3, and s is 0, 1, 2, or 3, this is s, this is r. What is 0 squared?
0.
0. 1 squared? 2 squared? 4 is 0. 4 is 0. and 3 is 9, which is 1. Does everybody see that? So the squares, if r is 0, 1, 2, 3, if r ranges from 0, 1, 2, and 3, r squared ranges 0, 1, 0, 1. For the same reason as s ranges from 0, 1, 2, and 3, s squared ranges from 0 to 1 to 0 to 1. And now take 1 second and work out all the sums of these numbers. In fact, you only have to work out this little piece of it because that has all the options. You have zeros and ones added with zeros and ones, and this is more zeros and ones, so that's just going to repeat the same pattern. It should take 3 seconds. What do you get? So I'm looking at r squared plus s squared, which means 0 plus 0, 0 plus 0. Zero, thank you, Alex. 0 plus 0 is 0. 0 plus 1? 1. 0 plus 1? And 1 plus 1? 2. So mod 4, just looking mod 4 at this equation, there is no number that is a sum of 2 squares mod 4 if z is 3. 3 does not occur as a sum of 2 squares mod 4. No 3's. If z is 3 mod 4, and sometimes people drop the mod if it can't cause confusion. So start getting used to me dropping the word mod. So 3 parenthesis 4 means 3 mod 4. Okay? Then z cannot be a sum of 2 squares mod 4. But if this equation had a solution in the integers, then you would just reduce that solution mod 4 and you'd get a solution mod 4. Let me say that again. If there were integers r and s, so that r squared plus s squared was z, then you just take that equation and you reduce it mod 4, and you'd get a solution to this equation mod 4. But there are no solutions mod 4 if z is 3 mod 4. So there are no solutions in the integers. Let me write that down. This is really important. This has a name. This is called a local obstruction. So let's keep this here. This is the key principle. Key principle. If there exists a solution z equals r squared plus s squared in the integers, in other words, I give you some number z. You find it as a sum of 2 squares. If you can do that in the integers, then you take that solution, you reduce it mod 4. Then there exists a solution to z is congruent to r squared plus s squared mod anything, in particular mod 4. The contrapositive is, if there's no solution mod 4, there can't possibly be a solution in the integers. But if z is congruent to 3 mod 4, then this has no solution. So this has no solution. Crazy? This has a name. This is called a local obstruction. It's a two-adic obstruction to solving this equation. Well, we're going to discuss the p-adic numbers soon. You just want to plant the seed to this. So the local, well, there's some local fields floating around, and we're looking for global solutions. Okay. Any questions on this proof of lemma 1? Yeah?
So, does it basically work for just 3, 4 at a time?
It's not because 3, so it turns out,
So we can't say like if C is congruent to 5 mod 6, then it can't be a solution.
let's look at 5 mod 6. Excellent question. Can we find more local obstructions? Are there other reasons that numbers can't be a sum of two squares? Excellent question. Let's look at this question. Maybe other obstructions? In fact, that'll be a good exercise. So here's, I'm not giving you enough exercises here. So exercise 1 for today. Make a table for r squared plus s squared mod 6. Okay? So you look at 0, 1, 2, 3, 4, 5. You look at 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, mod 6. So you'll do the same thing. R squared mod 6, S squared mod 6, and look at the sum. Okay, 0 squared, 1 squared, up to 5 squared. And then you say, you look, see anybody missing.
Is that due next Friday or this Friday? Question.
Any question from 1 week is due the Friday of the following week.
Okay, so this is due next Friday.
Next Friday.
Okay.
Things from last week are due this Friday. Okay? Make sense? So in particular, let's look back at our list of numbers that we saw and numbers that we didn't see. Here's the numbers that we did see. Here are the numbers that are missing. So multiples of 3 are missing, except for multiples of squares of 3. But multiples of cubes of 3, cubes of 3 are missing. 7s are missing. Why are 7s missing?
3 plus 4 is 7.
Because 7 is 3 mod 4. 3 is 3 mod 4. How about 11? 3 mod 4. How about 15? 3 mod 4. And it's 3 times 5. But 5 itself is okay. 5 is 1 mod 4. 13 is okay. 13 is 1 mod 4. 21 is 1 mod 4. But it's missing. It's 3 times 7. What is going on? Karen?
Multiples of 3 mod 4 are solution.
So certainly any integer that is 3 mod 4 is missing. Some multiples of 3 mod 4 appear. So I kind of don't want to give away the punchline. I kind of want you to discover it because it's such a crazy thing. You see, we asked a question about whole numbers, and the question will reduce to which primes, what the prime factorizations of those whole numbers are, which primes arise in the factorization, prime factorization. The question was not about primes, it was just about whole numbers. But the primes interfere. The primes tell you everything. All right. Well, so maybe the first question we should ask is which primes arise? So let's make this an exercise. Here's another exercise. I really want you to think about this. I don't want to give the answer, but this is famous work of Fermat, by the way, what we're studying now. Kind of unrelated to his last theorem, but kind of related too, because this is the motivation for asking this question. Exercise 2, take primes less than 100. There's not that many of them. How many are there? How many now? 15. How many?
Less than 100.
Less than 100. Definitely less, even less than 50, because half of them are even. What is it? 25? Maybe. Okay? Make a list of the primes less than 100, which are and which aren't sums of two squares. So certainly if you have a prime that's 3 mod 4, it's not going to be represented because no integer 3 mod 4 is represented. Do we get every prime that's 1 mod 4? That's what I want you to think about. Okay? So that's exercise 2. Make this table. Make this table and think about it. Gosh, I don't want to wait until next Friday to give away the answer here. But then it kind of takes away from this exercise because do this exercise for next class. I mean, hand it in as usual, but do the exercise for next class. Okay? Can I ask you to do that? This is for this Friday. Not to hand in this Friday, but just do it in time for this Friday. Okay. Here's what you'll find. I'm not going to tell you what you'll find. Let's play a little bit more with modular arithmetic, because modular arithmetic gets us to the heart of a whole lot of things that we want to understand. So more on modular arithmetic. More on modular arithmetic. Let's build up some technology. Let's build up some techniques. And then we're going to come back to this question and try to answer it completely. And it can be answered completely, and this is what Fermat did. All right, Fermat started messing around with modular arithmetic, and he noticed some funny things. So let's look at, give me a number to work as our modulus. 7, fine. So mod 7. And give me a starting number. 5, fine, so 5. Look at powers of 5. Let's look at powers of 5. Powers of 5. Okay, so 5 to the, so this is n, and 5 to the n. Now this seems like it's going to get really hard, right? We need to take huge powers of 5 and then reduce them mod 7. Well, let's see. So n is 0, 1, 2, 3, 4, 5. I don't know how much farther we have to go. 5 to the 0 is 0.
Is 1.
Good. Okay, just checking. 5 to the 0 is 1. 5 to the 1 is 5. 5 to the 4, 5 squared is 25. 25 squared is... Yes, okay, you guys actually know 5 squared is 625, but my point that I'm trying to make is that you don't have to know 625. You can do very, very small arithmetic. That's the beauty of modular arithmetic. Watch. 5 squared? What?
Because 21 is a multiple.
25 is 21 plus 4, and 21 is a multiple of 7. 5 cubed? Well, I don't need 5 cubed. I need 4 times 5. 6. Cool?
Yeah.
Makes arithmetic very, very simple. All right, finish the table. I don't know how far you have to go. 6, 7, 8, 9. Finish the table. Take 10 seconds. Who's got the next entry? Nobody has the next entry? What is it? 2. Why? Because 6 times 5 is 30. We already have 5 cubed. We want 5 to the 4th. 6 times 5 is 30. 30 is 2 more than 28. Okay, keep going. Karen, you're all done? Give me a thumb up when you're done. But you'd be teaching this in middle school. This is like easier than actual arithmetic. Okay, people are done. 2 times 5 is 10. 10 mod 7 is 3. 3 times 5 is 15. 15 is 1 mod 4. 1 times 5 is 5. 5 times 5 is 25, which is 4. Oh, wait a second.
Once you hit 1,
Yeah, once we hit a cycle. Of course we hit a cycle. We have to hit a cycle. Because eventually we're going to hit the same number. There's only 7 numbers that we can hit, 0 through 6. So we're going to hit a cycle. So we don't need anything 6 or higher.
It's just a ring of order 7, or a group of order 7.
It's some permutation. Yeah, the powers of 5 have permuted. I mean, we need to choose one of these. Let's say 5 to the 0 we forget about. So we start with 5. We take powers of 5, and it's just a permutation of 1 through 6. Why don't we ever get 0?
Is there no powers of 7 that are also powers of 5?
There are no multiples of 7 that are also powers of 5. The prime factorization of powers of 5 have no 7s in them, because the prime factorization is just 5s. So you'll never get 0. You'll never get a multiple of 7 by taking powers of 5, but you will get every other residue class. Weird. How about powers of 4? Take 1 minute. Compute.
Mod 7?
Mod 7. Give me a thumbs up when you're done. Okay. 4 times 4, 16. 16 mod 7. 2 more than 14. 2 times 4 is 8. 8 times 4, so 1 times 4 is 4. Now look at that. 4, 2, 1. 4, 2, 1. This time we didn't get all the numbers. We only got 1s, 2s, and 4s. We're missing 3s and 5s. What's that?
We stop at 3 because it's repeating itself from 4.
Yes, yes, we can stop at 3. It's repeating itself starting then. Right, once we hit 1, we know we're done because, yeah, it's always gonna, that's the same thing as raising it to the 0 power, right? Okay, anybody notice any patterns? Should we do another one? Should we take powers of 3?
5 is prime and 4 is not. It's not have one?
Okay, I don't know. Let's take powers of 6. 6 is not prime. It's kind of hard because mod 7, almost all the numbers are prime. 2 is prime, 3 is prime, 4 is not, 5 is, 6 is not. Should we take powers of 6? Do powers of 6. Sheep.
So I think like n minus 1 mod 7 is equal to 1.
N minus.
Any n minus 1 mod, the number 7 is going to be 1.
Say that again.
N minus 1.
N minus 1
mod 7
mod 7
is going to be 1.
Is, I don't understand what you mean by that. N minus 1 mod 7 is 1? So n is 2 mod 7? No, I don't.
Like if you take n
You mean, you don't mean n minus 1. You mean any number to the n minus 1.
Yeah.
So Devendro is making a conjecture that if you take any number, you raise it to the n minus 1 power. I'm sorry, Sheep is making a conjecture. It's a good conjecture though, you should take credit for it. That if you take any number, raise it to a power, mod 7,
Yeah.
you'll get 1. That's an interesting conjecture.
Oh,
It's definitely true in these two cases. Did people do powers of 6? What'd you get? Yeah, because so let's look at 6 to the n and n. 1, 2, 3, and so on. So 6 to the 1 is 6. 6 squared is 36, which is 1 more than 35. And then it's going to go 6 and 1, and 6 and 1. Here's n minus 1. Here's p minus 1. So by n minus 1, you mean p minus 1, where p is. So you mean raising something to the 6th power will always give you 1. I mean, I'm sort of putting words in your mouth, but I think those are the. Is that was that your conjecture? It's a good conjecture. Why is this happening? Should we have known that this had to happen? Maybe that's what you were going to say. 6 is also represented by negative 1. What are powers of negative 1? Negative 1, 1, negative 1, 1, negative 1, 1. Right? This had to happen. This had no other choice but to have period 2. Because negative 1 has period 2 in the integers before we take mod 7. Does that make sense? Okay. So indeed, this is a theorem, and this is Fermat's little theorem. Fermat's little theorem. If A is not congruent to 0 mod 7, of course powers of mod 7, mod P, any prime, if you take powers of 7, you're just going to get 0 the whole time. 0 times 0 times 0 times 0. Okay? If you take any other number and you raise it to the p minus 1 power, you raise any of these to the 6th power when p was 7, that will be congruent to 1 mod p. Okay? Is the statement of the theorem clear? This is called his little theorem, not as opposed to his last theorem. I think we can prove this. Here's a key observation. Let's prove this instead of taking too much time to discover a proof. Let me just tell you his proof in the interest of time. Let's see. here's the key idea, proof. Key idea. There's a variety of ways to do this, but here's one of my favorites. Look at 1 times A, 2 times A, 3 times A, and so on, up to P minus 1 times A. So let's do this. For example, P equals 7, A equals, give me some A. 4? Fine, let's do 4. Okay? So what is 1 times, so we need 1 times 4, 2 times 4, up to 6 times 4. 3 times 4, 4 times 4, 5 times 4, 6 times 4. So 1 times 4, 4. You'll see in a second what this has to do with, instead of taking the powers of A, I'm just taking the multiples of A. Something completely unrelated, or so it seems. 2 times 4? 1. 3 times 4? 5. 4 times 4? 2. 5 times 4? 6. Is Karen the only one doing this? Raise your hand when you know what 6 times 4 is. 3, okay, good. And what do you notice about these numbers? They're all of them, yeah. It's a permutation of all the numbers. Mod 7. Even though the powers of 4 do not reach every number, the multiples of 4 do reach every number. Why is that? So my claim is that these are all distinct. Claim is that K times A is congruent to L times A implies K is congruent to L. So the only way two of these multiples are the same is if the multiples are themselves the same. In other words, these are all distinct. That's my claim. Any idea why that might be true? Well, let's look at this. Let's look at the difference. So, what does this mean? This means K times A minus L times A has P as a divisor. I mean, this is congruent mod P. Depending. Exactly. So this is true if and only if P divides A times K minus L. But A is not a multiple of P, and P is a prime. So this integer is a product of a bunch of primes, but A doesn't have the prime P as a factor, which means this thing has to have P as a factor. This implies P divides K minus L, because A and P are co-prime. If A had a factor in common with P, then A would be 0 mod P. We assumed A is not 0 mod P. Does that make sense? Who's lost? She.
So they are using Euclid's lemma, right?
Yes. I'm doing things slightly out of order. I want to get to really juicy things, and then we start realizing, did we really prove this rigorously? Did we have reason to be able to say this? And the answer is, I'm going on your intuition from grade school about how primes work, but of course we want to prove that those things really are true. So we're going to circle back around to those issues. At the moment, I'm just going on your intuition that prime factors, on your sort of knowledge of prime factorization, heuristic though it may be. Okay? So you're right. In fact, the way most number theory courses go is that they prove a bunch of really, really annoying, obvious statements first, so that then they can prove really interesting statements and they can rely on, rigorous foundations. I'm sort of doing the opposite. I'm relying on your intuition for how primes work to try to get right to interesting things. But then we realize along the way, do we really know that this is true? How to prove things like this? And that will motivate us at some later point to go through and really pick up, fill in these gaps. Okay? So you're making an excellent point. Hopefully you will forgive. This is my viewpoint is you should prove these things rigorously when you have good reason to prove them rigorously. We now have good reason to prove them rigorously, so maybe it's time. But first I want to give you reason for why you should think about this. So what did we prove? If one of these the only way these two multiples can coincide is if the multiple was the same, but these multiples are all different. So these multiples, none of them coincide. And none of them are 0 mod p, none of them are multiples of p, because 1, 2, and 3 and p minus 1 are not multiples of p, and a is never a multiple of p. So they're all distinct. So 1 times a, 2 times a, up to p minus 1 times a are all distinct, non-zero mod p. They're not multiples of p. And there's p minus 1 of them. There are p minus 1 numbers. So what are these numbers mod p?
It should be 1 to p minus 1.
Yes. So these numbers, this is just some permutation. This is all the numbers 1, 2, up to p minus 1 in some order. In some permuted order. Does that make sense? And so what happens if we multiply them all together? So that's what we saw here, that the multiples of 4 are all distinct, and it's just some permutation of the numbers from 1 to 6. So 1 times a times 2 times a times 3 times a, all the way up to p minus 1 times a, is a product of all the numbers from 1 to p minus 1. So if this is congruent, mod p, to just 1 times 2 times 3 and so on times p minus 1. Cheek?
So when you say permuted order, what do you mean by that?
So when we looked at the multiples of 4, 1 times 4, 2 times 4, up to 6 times 4, we got the numbers from 1 to 6, but just not in order.
Oh,
They're just permuted around, mixed around. So if I multiply all of these numbers together, it's the same as multiplying the numbers from 1 to 6. It's all the same numbers, but multiplication doesn't care what order it comes in. Now what is this? Yeah, it's just p minus 1 factorial.
yeah.
And what is this? Again, there's p minus 1 factorial. But there's also a whole bunch of a's. How many a's? P minus 1 of them. Now we're almost done. I have to let you go. So let's unpack what this says. This says that p divides p minus 1 factorial times a to the p minus 1 minus p minus 1 factorial. I just moved things to one side. This is yet another way of, this is one of our ways of understanding what modular arithmetic means. But this factors as p minus 1 factorial times a to the p minus 1 minus 1. So p has to divide p minus 1 factorial times a to the p minus 1 minus 1. So p is a prime factor of at least one of these things. We have a bunch of integers, and their prime factorization contains p in it. Can any of the numbers here have p in it? Why? All of these numbers, this is 1, 2, 3, up to 6. None of those are going to be divisible by 7. So what must be divisible by p? This other part must be divisible by p, which implies p divides a to the p minus 1 minus 1, which implies a to the p minus 1 is congruent to 1 on e. And that is Fermat's little theorem.